Hello everyone, and welcome back to our journey through the R programming language. Today we're going to be introducing and going through some of the basic calculations in R associated to 5 of the most commonly used probability density functions that are often used in a hypothesis testing. Those are the z, t, chi-square, f, and chi distributions. Just as a heads up, the z, t, chi-square, and f distributions do not require any packages to be installed in the base system of R, but the chi distribution, on the other hand, does require some packages to be installed. In this video, we're not going to be focused on when you would use each of these distributions and some of the applications for each of them. We'll save that for a later time. So we're just going to be focused on how to calculate, say, quantiles and probabilities for each of these distributions, which are then going to be used for critical values and p-values for the associated hypothesis test, provided that you have identified one or many of these distributions as appropriate for that particular hypothesis test. The first distribution that we're going to be taking a look at would be the z distribution, which is oftentimes called the standard normal distribution, which is just a normal probability density function whose mean is 0 and its standard deviation is equal to 1. Oftentimes, people only consider the z-distribution on the interval from -3 to 3, which is often due to the fact that the empirical rule is often taught in institutions, but sometimes going from -5 to +5, or even more further beyond the mean of 0, is sometimes appropriate, depending on what you're analyzing and the sensitivity to outliers that you want to sort of instantiate. So what I've already gone ahead and done here is I've defined a discrete vector from -5 to 5 with partition size of 0.1, because since this is a continuous distribution, we need a discretized version of the domain to plot it, to analyze it. And here, this is the infamous probability density function for the standard normal distribution. And here is just some plot functions to sort of make it look a little bit more nicer. In case you don't know some of these plot characteristics, x1 is the domain, fz is the range, main is the title, type is the line type that you're plotting, for example, dotted lines, solid lines, jagged lines, circles, dots, or so on. LTY is the line type, LWD is going to be the line width, and COL is the color that you're going to be plotting with. So if we give each of these lines a run, notice that that's going to produce a discretized version of the standard normal distribution. Obviously, if you want this graph to be a little bit more smoother, you're going to change this increment 0.1 to something a little bit more smaller, say 0.01, but nonetheless, the graph is just there to sort of give you some idea of what you're actually working with. So oftentimes when you're going to be doing a hypothesis test, you're often going to be working with what is called an alpha value, which is sometimes referred to as the probability of making a type 1 error in your hypothesis test. Let us assume for the sake of discussion that we're going to be working with an alpha value of 0.07 or equivalently 7%. So obviously there's a few quantiles that would be associated to this. For example, if I want, for example, 7% of this distribution in this particular curve, obviously 7% of the data is going to lie to the left of some number. Also, 7% of the data is going to be lying above some number, say in the right-hand tail. And if we divide this alpha value half in the left and half on the right, then there's going to be two symmetric values on both sides of this distribution. So let's see if we can first calculate each of those quantiles that I've mentioned. So for example, if you want that lower quartile where you want, for example, 7% in that left tail, so this would be, for example, your left tail alpha value, then you could just do Q norm of alpha, and then you can just tell it which tail do you want to be in. So we want it to be in the lower tail or the left tail, so we're just going to be saying lower tail is equal to true, and that's going to be what we're eventually going to call our left critical value for our left-tailed alpha. So in terms of its interpretation, 7% of the standard normal distribution lies to the left of negative 1.4758 approximately. And obviously, if we want to do, for example, a right tail alpha, then what we can do is we can do Q norm of alpha, and we want this alpha to be in the right tail, or we're just going to say lower tail is equal to false. So that means 7% of the data is going to be over here somewhere, and according to R, 7% of the data is larger than 1.4758. Now you should be able to notice here that the left and the right critical values are just opposites of each other, and that's just due to the fact that the z distribution is symmetric about its mean, which in this case is equal to 0. Now, sometimes we would like to split our alpha into two. In particular, we would like a two-tailed alpha value. So instead of 7% being in the left tail or 7% being in the right tail, we're going to split that 7 in half on the left and on the right. So how would you get those associated quantiles? So what we can do is we can do Q norm of alpha over 2, and lower tail is equal to true, so that's going to be that lower two-tailed critical value. And then we're going to have Q norm of alpha divided by 2, and lower tail is equal to false, and that's going to be our upper-tailed critical value for our two-tailed alpha value. Right, and those are the four most common ways to calculate quantiles for standard normal distribution in the hypothesis testing world. Now, for probabilities, we're usually going to be given what is called a test statistic. So let's assume that we have a z test statistic of, let's say, 2.18, and let's assume that this is what we're going to call a two-tailed test statistic. And again, we're not going to go through what these mean in this video. That's more of a statistical conversation rather than a programming one. So a two-tailed test statistic is the probability of getting this test statistic or more in favor of what is called the alternative hypothesis. So again, we're wanting to find the probability that we're bigger than 2.8, so in this right-hand tail, and also less than its opposite, which is going to be negative 2.18. So what we can do is we can do the probability associated to that particular z-stat value. For example, z-stat, let's say lower tail is equal to false. So what this is going to calculate the upper tail probability associated to 2.18. So this is the probability that a z random variable is bigger than 2.18. We also want the probability that we're less than negative 2.18. But since we're in a symmetric distribution, we can simply just multiply this probability by 2, and that's going to give us a right tail and our lower tail in the same exact statement. And according to this, if we calculate this out, provided that I've actually defined our test statistic z-stat, then we're going to see that our probability of getting a test statistic equal to 2.18 or more in favor of the tails is going to be approximately 2.926%. And sometimes this is called the p-value associated to this test statistic. The next distribution in sequence is known as the t-distribution, sometimes called the student's t-distribution. So to use the t-distribution, you need to have what is called a degrees of freedom. Typically, if you're working with just one sample and you're trying to make inferences on the population mean, for example, then we would be using a degrees of freedom equal to the sample size minus 1. But generally speaking, the degrees of freedom could literally be anything, so definitely make sure you understand the hypothesis test that you were working with in order to accurately choose the degrees of freedom. Because for each degrees of freedom, you're going to have a different t-distribution, unlike the z-distribution where there's actually only one z-distribution. So just like I had with the z-distribution, I've defined my domain to be from -5 to 5 in an increment of 0.1. I've chosen a degrees of freedom of 9 just for the sake of exemplification. And here is the long but also famous probability density function for the t-distribution with v degrees of freedom or nu degrees of freedom, depending how you read that. Inside of this probability density function, we of course have the gamma function, which some of you probably already know is just the extension or one of the extensions of the factorial function, and then the rest of the probability density function, which does have some resemblances to the z distribution. In case you already do not know, as you increase the degrees of freedom, the t-distribution will get closer and closer to a z-distribution. So if you make this degrees of freedom equal to, say, 1 billion, you probably will not be able to see a lot of the difference between that t billion distribution and this associated z distribution. So let's just give these codes a run just to sort of see what the t-distribution looks like. So if we run those 4 lines of code, as you can see, the T9 distribution does have that sort of bell-shaped curve, but in case you do not already know, the t-distribution does typically have wider tails than the z-distribution does. And that's often associated to the fact that, for example, if you're testing hypotheses on the mean, we usually have to approximate the population standard deviation with the sample standard deviation, and hence we need to account for that particular variation, which is one of the reasons why the tails of the t-distribution are a little bit more wider than that of z. So just like with the z-distribution, we first need to state an alpha value that we plan to work with for our particular hypothesis test. Let's assume that we're going to be again working with 7%. So let's calculate those lower tail, upper tails, and both of those two-tailed critical values associated to this. So just like we had for the z-distribution where we were using the function qnorm, for the t we're going to be using the function qt. So for example, the left tail critical value is given by qt. So let's just do qt. And then our alpha value, our degrees of freedom. And where do we want that tail? We want that to be in the lower tail. So that's going to give us our left critical value. So this is going to be our left tail critical value. Similarly, qt alpha nu, and then lower tail is equal to false. This is going to be our right tail test critical value. And then we have our qt alpha over 2 v lower tail equals true, and our qt alpha over 2 nu lower tail equals false. So this is going to be our two-tailed test, the lower one. And then this is going to be our two-tailed test, the upper one, right? Because if we have a two-tailed test, we have a lower value and an upper value that sort of dictates where that alpha is located. And if we give these 2 lines of code a run, we have negative 2.06 and 2.06 approximately for our degrees of freedom. Now again, if you choose a different degrees of freedom and a different alpha value, you will get different values for each of these critical values. So keep that in mind. So just like before, if you're working with the t-distribution, you probably also have a test statistic. And if it's associated to a t-distribution, it's probably called a t-test statistic. Let's assume that we're working with a t-test statistic of negative 1.76, and let's assume that this is a two-tailed t-test statistic. That means we want the probability of getting less than negative 1.76 and also bigger than its opposite of positive 1.76. So that's often called the p-value associated to this test statistic. And just like we used p-norm for normal, we're going to be using pt for the t-distribution. So we're going to be doing the probability for this particular test statistic. Keep in mind that this is the left-tailed test statistic since it is negative. Therefore, we do not need to negate it. We have to feed it the degrees of freedom. We need to tell it where that test statistic is located. In this case, it's going to be a lower tail. So if we evaluate this particular probability, provided again that you have defined this test statistic t-stat, if we give that a run, notice we have that value of 0.0561. Now keep in mind we did not multiply by 2 here, therefore this is not the two-tailed probability. This is just the probability that we're less than negative 1.76. So if we want the two-tailed probability, we would just multiply that by 2, which is going to be 0.1123, which is the probability that we get a test statistic of equal importance or of greater importance and significance in regards to our alternative hypotheses. So that's how you would calculate critical values and p-values and probabilities and quantiles for a t-distribution for some given degrees of freedom. The next distribution that we're going to be taking a look at is the chi-squared distribution. If you already know some of the applications for Z and T, you probably know that Z and T are often used to make inferences on the mean. The chi-squared, on the other hand, is associated to making inferences on the variance. As you should already know, variance cannot be negative, therefore the distribution of the chi-squared distribution also should not be negative as well. That's why we've chosen the domain for this next distribution to be on the positive end, in particular from 0 to 25. Now, in terms of why we've chosen this 45 as our upper limit for our domain, that is precisely dependent on the degrees of freedom that we've been using for this particular chi-square distribution. So typically a good range for graphing a chi-square distribution is usually 3 times the degrees of freedom, but it really depends on that magnitude and what type of information you sort of want to encapsulate in that particular graph. Underneath this degrees of freedom and this domain definition, we have the probability density function for the chi-squared 15 distribution. And as usual, if you have a different sample size, you're going to have a different degrees of freedom. And for one sample, that's typically just like the t, n minus 1. So let's just give these lines of code a run just to sort of see what the chi-square distribution looks like, just in case you already do not know. So as we see, we have a sort of bell-shaped curve for the chi-square distribution, and this will be skewed to the right. Right. So again, the larger the value of our degrees of freedom, the more skewed to the right this will become, and the higher the value, this sort of mode of this distribution will be pushed to the right as you increase that degrees of freedom. So, just like for the z and t, we're going to be working with some alpha values. So let's choose the 7% alpha value that we chose for the other ones, just to sort of have some uniformity here. We're going to have, for example, a lower tail critical value, an upper tail critical value, and the lower and upper values for a two-tailed hypothesis test. We're going to follow the same exact conventions, just like we did for z and t. So we used qnorm and qt for the quantiles of a z and t distribution. So just like for those, we're going to be using a q chi-skew distribution, which is just short for a q chi-squared distribution. So for example, q chi-sq is going to be our value. So we're going to have our alpha value that's not going to be divided, our degrees of freedom, and then we're going to be lower tailing that to be equal to true. So this is going to be our lower tail or our left tail critical value, which is again always going to be positive because chi-squareds can't be negative. Then we're going to have q chi-skew, and then alpha nu, and then lower tail is equal to false. This is going to be our right tail or a one-tailed right critical value. Keep in mind the chi-squared is not symmetric, so do not be surprised that you do not see any symmetry between these numbers. But they are symmetric in regards to the probability, right? Because we have alpha to the left and alpha to the right of each of these respectively. Similarly speaking, if we divide our alpha by 2 and split half of it on the left and half of it on the right, we're going to have q chi-skew of alpha over 2 v, and then lower tail is equal to true. So this is the two-tailed lower critical value, which is 6.72 approximately, and q chi-skew of alpha over 2 nu, and then lower tail is equal to false. This is going to be our two-tail upper critical value, which is approximately 26.2985 approximately. Just like the z and t, you could also have, for example, chi-squared test statistics, which you can make inferences about, for example, the variance or maybe even independence between categorical variables and several other things. So let's name our chi-squared test statistic. Let's name it just C2 stat for chi-square stat. And let's assume that this is equal to 30.8. And let's pretend now it's a right-tailed test statistic, right? So for example, is this significantly large? And if so, how large is it? So that means we're only going to be calculating a right-tailed probability for this particular value. So that p-value would be calculated just like p-norm and pt. We're going to be using p chi-skew here. For our individual test statistic, our degrees of freedom is chosen to be v, and then lower tail is going to be equal to false, and that is going to be our value for our p-value, which one can argue is relatively small. Right? And usually you're going to be comparing this p-value to an alpha value, but again, we won't get into the statistical theory of why we actually do that. Here, we're just focused on the implementation. The next distribution is often built from dividing two chi-squared random variables. So since chi-squared random variables cannot be negative, f random variables can also not be negative as well. Since chi-squared has a degrees of freedom, and we're dividing two chi-squared random variables, that means we're going to have 2 degrees of freedom for an f random variable. The top chi-squared random variable is going to have a degrees of freedom, which we're going to be calling v-top or new top. And the bottom chi-squared random variable is going to have its degrees of freedom, which we're going to be calling v-bot or new bot. In this case, we have 17 and 14 respectively. Most of the time, the F distribution is going to have a smaller non-zero domain, I guess you could say. That's why we've only gone from 0 to 4 compared to, say, 0 to 50, like in the last example. The F distribution does have a quite complicated probability density function with a few instances of the gamma function, but nonetheless, it does have one, which is pretty nice. So, what does the F distribution look like? So let's just give these lines of code a run and notice that this is our F distribution. It practically has the same exact shape as the chi-square distribution, but as I've already mentioned, it is supported on a more smaller domain. And this is the F1714 distribution, which importantly is different from an F1417 distribution. So if you rearrange these degrees of freedom, you will get a different shape, right? So for F distribution, you need 2 degrees of freedom and the order matters, right? Typically speaking, if you're comparing variances, the larger variance goes on top, the smaller variance goes on bottom, and those variances have their associated sample sizes, which are, say, n1 minus 1 and n2 minus 1, which gives you those degrees of freedoms. So, just like for the z, t, and chi-squared, we're going to have some left, right, and two-tailed lower and two-tailed upper critical values to calculate. So let's choose our alpha value. Let's go with the classical 5% alpha value, and let's calculate our lower critical value. So just like we had for q norm, qt, and q chi-squared, we're going to have qf for quantiles. So we're going to have alpha, v top, v bot, and then lower tail is equal to true. We're going to have qf alpha, and then v top, v bot, and then lower tail is equal to false. So that is your lower tail and upper tail, or left tail and right tail critical values for one-tailed tests. And then for our two-tailed lower and two-tailed upper, we're going to have QF, so we're splitting our alpha into 2. Again, V top, V bot, lower tail equals true. And then QF alpha over 2, V top, V bot, and then the upper one, so lower tail is equal to false. So that gives you your lower tail and upper tail critical values for a two-tailed test. So for our F critical value, let's assume that we have an F stat equal to, let's assume it's equal to, say, I don't know, 5.46 divided by 3.12, right? And let's assume that this is a right-tailed test statistic. That means we need to calculate a right-tailed probability. So just like we have P norm, PT, and P chi-skew, we're going to be doing PF for probabilities for the F. So we're going to be feeding that the F test statistic. Again, V top and V bottom, those do not change. And then lower tail is equal to false since we're in the right tail, and that will give you your associated probability for that particular F test statistic. The next distribution that I want to introduce is called the chi distribution, which often isn't taught in the sequence of the previous 4. The reason I want to introduce the chi distribution is because sometimes it's more convenient to deal with the chi distribution directly. For example, the t distribution that we've already talked about, which has several different examples, is calculated from dividing a standard normal random variable divided by a chi random variable, not a chi-squared random variable. So in some sense, we have already been working with chi random variables up to this point. Also, if you want to make inferences about the variance of a population, you would be using a chi-squared, but sometimes you would actually just want to make inferences about the standard deviation directly. In that case, you would be using a chi distribution. So as already mentioned, the chi distribution is not in the base package of R, but you could get the answers that we're about to do from the chi-squared by applying square root operations. But if you just want to work with similar functions for the chi distribution, like we did for the z, t, chi-squared, and f, you can install the package add habitat lt and then include that library in your base program. So from there, we're going to define our domain, our degrees of freedom, and the probability density function for a chi distribution. and give that plot a go. Just like the chi-squared distribution, the chi-distribution also is going to be a right-skewed distribution, but notice that it's not as situated close to 0 compared to the chi-squared, and that's due to the fact that we're taking the square root of that distribution. So once you install these packages, then you can use similar functions to that of, for example, qnorm, pnorm, qt, pt, and so on. So for example, if you want to calculate the left tail critical value for chi, you can use QCHI. So let's assume that we want to work, for example, let's choose an alpha value of say 0.06. So we can use Q chi for just the chi distribution, and then use alpha, our degrees of freedom, which is chosen to be equal to 12, and then lower tail is equal to true. And then q chi alpha, nu, and then lower tail is equal to false. So these are our left tail and right tail chi critical values. And then we can split that alpha in two for the same exact reasons before to get our lower and upper two-tailed critical values. So we can do q chi of alpha over 2, nu, and then lower tail is equal to true. And then q chi alpha over 2, nu, and lower tail is equal to false. Okay, so those would be your associated critical values for a chi distribution. And you can define, for example, a chi test statistic. Let's assume we're working with 2.17, and let's pretend that this is a left tail test statistic for the chi distribution. That means we would be using, just like p norm, pt, p chi square, and pf, we would be using p chi for this particular test statistic. The degrees of freedom is set, and we want a left tail, so we're going to be doing lower tail is equal to true. And that would be a p-value associated to the chi distribution. There are several other distributions aside from the z, t, chi-square, and f distributions, and as already mentioned, all of these are typically based on the assumption of normality, or at least to some degree. So I hope you enjoyed this video, and I'll see you in the next one. Take care.